Alright, kiddos, hope everyone's doing well. Let's see if we can gain some ground on this area under a curve / definite integral. So we've been talking about the definition, limit definition Riemann sums, using this kind of elaborate process to find area under a curve. So let's use a specific example. So I want to find this particular area from 0 to 5 underneath, and let's just stick with the plain old squared function. Okay, so we're going to take the area from 0 to 5 underneath that squared function, and I want to find the area, right? So it's this part up in here that I want to find. How big is that? Let's first look at this applet that I think will be helpful, and it's from St. Louis University, which is really a great little applet they've created. So in this particular applet, what we're able to do is see how we move from an approximation of that area from 0 to 5 underneath the squared function. And here we're just using 5 rectangles. Well, what if we used 50 rectangles? Oh, we get a much better value, 42, almost 43. What if we use 500 rectangles? What if we use 5,000 rectangles? And so as we add more and more rectangular areas together, we get a better approximation than we would if we were to just use 5 rectangles, right? And so to turn the approximation into an exact number, instead of using, oops, too big. Instead of using just 5 rectangles, we're going to sum the area of not even 50, not even 500, but really an infinite number of rectangular areas, okay? So that is how we get an exact area under the curve from an approximation. We let the number of rectangles expand infinitely. Okay, so let's actually pull this off here. Let's see what we're going to do. So the first thing we want to set up is this limit definition, Riemann sum, infinite Riemann sum definition. So remember that, oops, here's what we're working with so far. That area, right, which is a definite integral, so in this case 0 to 5, underneath the squared function, is equal to the sum from 1 to n of rectangular areas. And the areas are delta x, which is the base of each of those rectangular areas, times the heights, which are f of t sub I being the tags, right? But as it stands, it's not the area, it's just an approximation. So turn it into the area. We want the limit as the number of rectangles goes to infinity. Okay? So this right here is the area under a curve. With the limit up front, it's exact. Okay? So what we need to do is, for this particular problem, we need to get exact pieces. So I'm going to start by, there are basically 3 things we need. We need the bases, we need the heights, and then the heights give us the tags. Okay, we need the bases, we need the tags, and then that gives us the heights. Heights being f of t sub i's. Okay, so sorry about my pen not working so great. Let's first start with the bases, the delta x, right? So my interval from 0 to 5 is 5, right? And if I'm going to cut that into n rectangles, and I'm just going to show 4 rectangles here, just so you get the visualization. Remember, they're an infinite number of rectangles. I can't possibly draw that. But each of those delta x's is going to be 5 minus 0 over n, right? Length of the interval 5 over n number of rectangles, right? Of course, n is a number of rectangles, right? That's always the case. Okay? So what that means is each of the common bases of those n rectangles is 5 over n. Okay? N rectangles cut up the interval of length 5 into n rectangles. Each of the bases, which will be the same, will be 5 over n. Now those common bases, delta x, which is 5 over n, give us the tags, right? So what I'm going to do to find my tag is I'm going to start over here at 0, and I'm going to jump to my first, let's say, right tag, right? And since the delta x is 5 over n, that leaves me to 5 over n, right? I'm going to jump to my next tag, which is going to be 10 over n, right? Jump to my next tag, which is going to be 15 over n, etc., etc. Right, so the first tag is 5 over n, the second tag is 10 over n, third tag is 15 over n. Therefore, my ith tag, remember I is the index, starts at 1, goes to n, is going to be 5i over n. Right? And in general, if we're starting at 0, the tag, t sub I, will always be delta x, which is 5 over n in this case, times I. If we're not starting at 0, it will be our a value, whatever the lower limit of integration is, plus delta x times I. Okay. Regardless, those tags, if you recall, get thrown into the function to determine the heights, right? So 5 over n gets squared, that's my height. 10 over n gets squared, that's my height. 15 over n gets squared, that's my height. So all my heights are going to be each tag, the ith tag, plugged in a function, which is the square function, right? So the height of the ith rectangle is the quantity 5i over n squared. Okay. Now I can plug values in, right? So now what I can do is I can, instead of delta x in here, I can replace that with 5 over n. Instead of f of t sub I, the heights, I can replace it with 5i over n, the quantity, squared. So for this particular example, I'm going to start a new page. The area that we're looking for, 0 to 5 under the squared function, is equal to the limit as the number of rectangles goes to infinity of the sum of their areas from 1 to n, of the bases. Now each of my bases, remember, is 5 over n. There's my base, and my heights are each of those tags thrown into the function squared, so that gives me quantity 5i over n squared. Okay. There's my setup. Right, I've set up the opportunity to now try to calculate this area. So what I'm first going to do in order to calculate it is I'm going to clean it up, what's in the sigma. So if I square 5i over n, I get 25i squared over n squared times another 5 over n. So we end up with is 125i squared over n cubed. Okay, all I did was I just cleaned that up to get this. Okay. Now, I have to compute that. So to compute that, what I can do is I can take out this and this term, and the rest I will substitute. So let's first take those out. So I'm going to take out, in front of the sigma, limit as n is going to infinity, I have 125 over n cubed. Now the reason I can take them out is because this summation has an index of I, which has entirely nothing to do with 125, nor does it have anything to do with n over n cubed. Okay. What I'm left with is, from 1 to n, the sum of the I squareds, right? Which we've been developing has a nice little formula that I can substitute in for the sum of the I squareds, right? 1 squared plus 2 squared plus 3 squared plus 4 squared plus dot 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 plus n squared. Now that is equal to sum of the I squareds, that is. The limit comes along for the ride. I got a 125 over n cubed, and the sum of the i's squareds is equal to, well, it's equal to a lot, but what we've established is that sum of the I squareds from 1 to n is equal to n times 2n plus 1 times n plus 1 all over 6. Right? However, what we've been establishing is we don't need to know all of that. What we need to know essentially is that the sum of the I squareds, sure, there's a 6 on the bottom, we need that. But we only need the leading term, the highest degree term on top. The way I'm going to get that is by multiplying n times 2n times n, and that leaves me with a 2n cubed. And then there's a whole lot of other stuff, plus, blah, 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 plus, blah, blah, plus, and then eventually there's a plus 1. But I don't care about that stuff, okay? And you'll see why I don't care about it in a second. I'm going to come down here, I'm going to clean up what I have here. I get a 2n cubed times 125, that's what, 250, I believe. Right, and then over 6n cubed, oops, running out of room here, right? And here's why I don't need all the other stuff on top, okay? If I'm evaluating the limit as n is going to infinity, the way in which we do that for a rational expression is by considering the highest degree term on top over the highest degree term on the bottom, okay? That's it. Everything else is inconsequential if we're examining the limit as n is going to infinity. And that's why I don't really need all this stuff over here. I don't need to know when multiplied out, right, what all that ends up being. All I need to know is just it's 2n cubed for my leading term. Everything else doesn't matter that much. Okay, so now I'm going to do this out actually. I end up with the n cubed over n cubed canceling. 250 over 6. What does that end up being? For, oh, I'm taking the limit. Sorry, the bell's ringing, rushing through this. 250 divided by 6 is what, 4? 240. There's 10 left over. 41. And 6, what's that, 4? 2/3. Okay. Check that. I'm not really thinking straight right now, but I believe that is what 250 divided by 6 is. Okay. Which is the area under the curve. If you recall, moving back to the original problem, the squared function from 0 to 5. Okay. That's that. Hope you enjoyed it. Sorry for being rushed towards the end, but I gotta go to class. Have a great day. We're gonna start with this, continue with this tomorrow. Bye-bye.